You know, when we picture a master diagnostician at work, we usually focus on, like, that big aha moment.
Oh, right, the brilliant deduction. We culturally romanticize that epiphany for sure.
Exactly. A doctor looks at a chart, notices one weird lab result, and suddenly, boom, the whole medical mystery is solved.
Right, the moment the pieces just effortlessly click together into a perfect, neat picture.
But, I mean, we completely ignore the invisible process that actually makes that moment possible. We ignore the 50 times the doctor probably second-guessed themselves right before speaking up.
Yeah, that's so true. We treat diagnosis as this straight line from, seeing a symptom to prescribing a cure.
Right.
But in reality, true medical reasoning is incredibly messy. It's iterative, and honestly, it's fueled by self-doubt.
And that internal debate is actually the secret sauce. So today, for our deep dive, we are looking at a massive attempt to bottle that secret sauce and, well, feed it to artificial intelligence.
Which is just a wild concept. We're diving into this really fascinating research paper titled Improving Clinical Diagnosis with Counterfactual Multi-Agent Reasoning.
And this comes from a huge collaboration, right? Researchers at UIUC, Jacobi Medical Center, Beth Israel Deaconess, and Learning Machines.
Yep, a really heavy-hitting group.
So our mission today, as we take you on this deep dive, is to unpack how these researchers are attempting to teach AI to think. And specifically, to doubt itself, just like a human doctor does.
It's a dense paper. I mean, it is filled with data sets, architectural diagrams, and some really intense real-world medical case studies.
But don't worry, because whether you are just catching up on AI developments or maybe prepping for a tech med meeting, or you're just insanely curious about how machines learn,
We've got you covered.
Exactly.
Right.
We are going to give you a shortcut to understanding this massive shift in clinical AI, and we're going to do it without drowning you in technical jargon.
To really appreciate the solution here, we first have to thoroughly understand the trap.
Right, the fatal flaw in how both humans and machines currently make decisions when the stakes are just, at their absolute highest.
Okay, let's unpack this. If you walk into an emergency room today with, say, a severe headache and a fever, you want the doctor to figure out exactly what is wrong.
Obviously. But diagnostic errors are still a massive, pervasive issue in healthcare. They lead to delayed treatments or even preventable harm.
And a major culprit behind those errors is a cognitive trap called anchoring bias.
Anchoring bias. Okay, what does that look like in practice?
Well, it happens when a clinician over-relies on their initial impression. They see that fever and headache, they make a quick hypothesis, say the flu,
Okay, makes sense.
and then they mentally lock in. When new contradictory evidence appears later, like maybe a strange stiffness in your neck, they basically refuse to update their initial hypothesis.
Wow, so they just
explain the new symptom away to fit their original narrative.
That is so common. It's kind of like a bad TV detective who decides the butler committed the crime in the first 5 minutes of the show.
Oh, that's a great analogy.
Right. And then, for the rest of the episode, the detective completely ignores the muddy footprints leading directly to the gardener, all because they've already anchored to the butler. They committed to a narrative way too early.
That phenomenon is exactly what is happening with current large language models, or LLMs, when they're applied to medicine. They act like overconfident novices.
Wait, really? The AI falls for the exact same human bias?
Completely. Most AI models currently use a standard method called chain of thought prompting to reason through a problem. You give the AI a patient's medical file, and it is supposed to think step by step.
Which sounds good in theory.
It does. But the critical flaw is that they reason over a completely fixed set of clinical evidence.
So they look at the file once, make a gut guess, and then just use their massive vocabulary to generate a very plausible-sounding story to back up that first guess.
Exactly. They're essentially just finding evidence to prove themselves right, rather than rigorously testing if they might be wrong. They rarely stress test their own theories.
Because they don't have that self-doubt.
Right. Now, in medical school, human doctors are explicitly trained to break this exact habit through a technique called counterfactual questioning.
Counterfactual, meaning contrary to the facts, thinking about what isn't there.
Yes. Medical students are taught to actively look at their working diagnosis and ask, how would my diagnosis change if this key symptom was actually missing?
Oh, interesting.
Or what if this lab result came back completely different? It forces a systematic, critical evaluation of the evidence. It breaks the psychological anchor.
But the problem the researchers identified is that current AI simply doesn't do this automatically. It just plows ahead with its first idea.
Exactly. So since human doctors use these what-if scenarios to break their own anchoring bias, these researchers decided to build an AI system that forces language models to mechanically execute that exact same process.
They literally engineered self-doubt into the code.
They did. They built a multi-agent framework designed entirely around forcing the AI to ask, what if not?
I really want to know how this architecture actually operates when a patient's file is loaded in. Because it's not just one giant AI brain trying to know everything about every disease, right?
Far from it. The system starts with a triage agent.
A triage agent, like an intake nurse at a hospital.
Exactly like that.
Yeah.
When a complex clinical case is presented, this triage agent analyzes the initial symptoms and assigns a custom team of AI specialists.
Oh, wow. So if the file mentions, like, breathing issues and strange blood work,
Then the triage agent might pull in an AI pulmonologist, an AI hematologist, and an AI radiologist.
so we basically have a specialized medical board.
Right. And these assigned specialists first work independently to generate domain-specific reports. The radiologist bot analyzes the imaging data. The hematologist bot looks at the blood work.
Okay, that makes sense.
Then they converge to begin a multi-round discussion. But the true innovation of this framework happens during this debate. It's a process the paper calls counterfactual case editing.
Okay, here's where it gets really interesting. I was reading through this part of the methodology, and I have to make sure I'm understanding the mechanics correctly. The AI is basically rewriting the patient's medical history mid-diagnosis.
It is, yeah.
Like, it's actively deleting or mutating the real symptoms just to see what happens in a parallel simulation.
That is the exact mechanism. To rigorously test their theories, the specialist agents use what the researchers call target evidence operations.
Target evidence operation.
Right. There are 6 specific ways they edit the patient's case to test the waters.
Walk us through those.
Sure. They can remove a finding entirely from the file. They can negate it, which means explicitly stating a symptom is absent.
Like, the patient definitely does not have a fever.
Yes. Then they can replace it with a different symptom. They can weaken its severity, intensify its severity, or, and this is wild, insert a completely new hypothetical clinical finding.
That is wild. They're running parallel universe simulations of the patient. Like, what if the patient didn't have a fever? What if the cough was actually much worse?
Exactly. It's an explicit, aggressive, evidence-checking step.
Yeah.
Instead of just arguing over the original text in the file, the bots are forcing a logical test.
Oh, I see.
They're saying, if I'm right that this patient has disease X, then symptom Y must be the root cause. Let's completely delete symptom Y from the file and see if my confidence in disease X drops.
Okay, I see the logic there, but I gotta ask, if these specialist bots are just playing around with alternate realities, deleting real symptoms and inserting fake ones,
Yeah.
how does that actually generate a real mathematically sound diagnosis for the actual patient sitting in front of them? I mean, they need some kind of scoring system to anchor this chaos.
They absolutely do, and that is the core metric of this entire system. The researchers call it the counterfactual probability gap, or CPG.
The CPG. Okay, let's break down how this math actually works for you listening.
So the counterfactual probability gap measures exactly how strongly a specific piece of evidence supports a diagnosis. It calculates this by looking at the change in the AI's mathematical confidence before the edit and comparing it to the confidence after the edit.
You know, I'm picturing this like playing a game of Jenga with the patient's symptoms. The tower is the final diagnosis.
That is a perfect way to visualize it. I love that.
Right, so every symptom is a wooden block. The AI builds a tall tower and says, I am 90% confident this tower is pneumonia.
Okay, I'm with you.
But to prove it, the framework forces the AI to start pulling out blocks. So it pulls out the fatigue block, the tower wobbles but stays up. The AI is still, say, 85% confident.
Right, so the CPG score for fatigue is low. It's only a 5% gap.
Mm-hmm.
That block wasn't really structural.
Exactly. But then the AI pulls out the fluid in the lungs block.
And the entire tower instantly collapses.
Boom! The AI's confidence in pneumonia drops from 90% down to 10%. That is a massive 80-point gap.
Which means the CPG score is incredibly high.
Yeah.
That proves mathematically that fluid in the lungs was the structural linchpin of the entire diagnosis.
It forces the AI to show its mathematical work. It can no longer just output a smooth, plausible paragraph saying, I'm sure it's pneumonia.
Right. It has to say, I am sure it is pneumonia. And if you alter this one specific fact, my diagnostic model collapses. Therefore, this fact is the critical evidence.
I love the Jenga mechanic, but I do have to push back on the efficiency of this as a complete system.
Okay, hit me.
If we have a bunch of different AI specialists, the pulmonologist, the radiologist, the hematologist, and they are all pulling out different Jenga blocks, running parallel simulations, and arguing over their own probability gaps,
Yeah.
doesn't that just lead to a chaotic room of bots yelling at each other? One bot says the fever's the most important, the other says the blood work is. How does this actually result in a single, coherent medical decision that a real doctor can use?
This raises a really important question about multi-agent systems in general. Without supervision, bots will just argue in an infinite loop.
Exactly.
To solve this bottleneck, the researchers introduced a final layer to the architecture, which is a judge agent.
A judge agent, like a chief of medicine stepping into the room to stop the arguing.
Precisely. The system is designed so that the specialists never actually have to reach a perfect, unanimous consensus.
Oh, they don't?
Nope. They discuss and run their counterfactual edits for a set number of rounds, generating a ton of valuable CPG data. When the rounds are up, the final judge agent steps in.
Okay, and what does the judge do?
It synthesizes the entire discussion history, But more importantly, it looks objectively at the CPG scores.
Hmm.
It sees which bot's arguments were actually backed up by the math when the Jenga blocks were pulled.
Ah, I see.
The judge agent then makes the final, evidence-grounded decision based on that hard data.
That makes a lot of sense. It is exactly like having a senior attending physician review the chaotic notes of all the medical residents before signing off on the patient's chart.
It really is.
So the theoretical framework sounds incredibly robust, but, theory is cheap in artificial intelligence.
Oh, absolutely.
To know if this judge agent and these argumentative specialists are actually making better decisions than a standard AI, we have to look at the hard data.
And the researchers tested this relentlessly. They ran the framework across 3 distinct, highly challenging data sets to ensure it wasn't just a one-trick pony that only understood one specific type of medicine.
Walk us through these testing grounds. What kind of medical data were they throwing at this framework?
First, they used MIMEF, which is a massive data set of intensive care unit or ICU cases.
Okay, so highly complex, messy, high-stakes scenarios with a ton of overlapping data.
Exactly. Second, they used med case reasoning. This is a data set curated from complex, rare disease case reports published in PubMed. These are the medical mysteries.
The 1 in a million weird cases. Got it.
And third, they used ER reason, which consists of real-world, everyday emergency room cases. Fast-paced, limited information, high-pressure diagnostics.
So they covered the messy ICU trauma, the rare medical mysteries, and the everyday ER visits. That is a really comprehensive spread.
It really tests the limits.
And what kind of AI models were actually running this framework? Like, who was doing the thinking?
They ran the test across 7 different large language models to see how it scaled.
Right.
This included general open source models like Llama 3.1 8B.
And just to clarify for everyone, 8B means it has 8 billion parameters, which in the AI world is actually quite small and highly efficient.
Right. They also tested specialized medical models like 𝗲𝗄, all the way up to the massive closed-source frontier models like 𝗬𝗎CR1 and GPT-5 which run on giant server farms.
And we should clarify, standard AI models usually operate on what is called a zero-shot basis in these tests.
Yes.
Meaning they are handed the medical file cold. They are given no prior examples, no cheat sheets, no warm-up cases. They just have to read the file and guess.
Right.
Did the bots arguing and deleting symptoms actually beat a massive model just guessing cold?
The framework consistently crushed standard prompting across the board. It also drastically outperformed prior multi-agent baselines that just let bots talk to each other without the explicit counterfactual editings.
There is one statistic that really jumped out at me from the results. The Llama model, which, as we mentioned, is a relatively small, accessible model, saw a massive 13.2% improvement in diagnostic accuracy over standard zero-shot chain of thought prompting.
It's huge.
A 13-point jump just by forcing it to use this what-if framework.
It is a remarkable leap in capability. It proves that you don't necessarily need a model with 1 trillion parameters if you teach a smaller model how to reason effectively.
That is such an important takeaway.
And if we connect this to the bigger picture, the data revealed some truly fascinating quirks about how different medical environments require different types of reasoning.
What do you mean by quirks?
Well, for instance, in those complex rare disease cases from PubMed, the negate and replace operations caused the largest probability shifts.
Let me make sure I'm translating that. For the weird medical mysteries, the AI found the answer by actively proving a symptom wasn't there or by swapping a symptom for a different one.
Exactly. Rare diseases often hide behind misleading symptoms or red herrings. By negating those red herrings, the AI could strip away the noise and find the underlying rare condition.
Oh, it is brilliant.
But in the standard messy ICU cases from the MIM dataset, inserting new hypothetical information shook the AI's confidence the most.
Wait, why would inserting fake data be the key to solving an ICU case?
Because in an ICU environment, AI models become incredibly stubbornly anchored to common trauma presentations. They see ICU vital signs and immediately lock onto standard critical care diagnoses.
They just assume the worst, basically.
Right. The AI was so anchored that the only way the specialist could get it to reconsider its diagnosis was to literally inject new contradictory evidence to jolt it out of its tunnel vision.
That is so incredibly human. It is just like an overworked doctor seeing the same flu symptoms all day in a clinic.
Yep.
You just assume the 50th patient also has the flu, and you won't even consider another option unless someone violently points out a totally weird, bright red rash on their back. You need new data to break the mental loop.
The framework forces the AI to provide its own jolts.
I want to pause here because if you are listening to this, you might be wondering, why should you care about any of this?
Fair question.
Why does it matter that this framework works so incredibly well on a smaller open source model like Llama instead of just relying on the giant genius models from OpenAI or Google?
It fundamentally comes down to patient privacy and data security.
Right, because if you are a patient lying in a hospital bed, you want your medical data kept perfectly private.
Absolutely.
Hospitals are bound by strict laws like 𝗬𝗂. They cannot easily or legally take your highly sensitive medical history, your blood work, your genetics, and just beam it up to a giant centralized corporate cloud server to be processed by a massive AI.
No, it is a massive logistical and legal hurdle. But this counterfactual framework changes the equation completely.
How so?
That 13.2% accuracy boost means a hospital can take a smaller open-source model like llama, run it locally on their own secure internal basement servers, and still get diagnostic performance that rivals the giant cloud models.
Wow. It allows hospitals to run highly accurate, reasoning-capable AI privately. It bridges the gap between keeping your data safe and getting you the best possible diagnostic capability.
Exactly. It makes world-class AI diagnostics practically deployable in real-world hospitals.
Okay, so we know the accuracy goes up, we know the privacy is secured by using smaller models, but to truly understand how the AI's internal reasoning actually shifts under pressure, we need to step inside the virtual consultation room.
Oh, this is the best part.
We need to see an actual high-stakes case play out with this framework.
The researchers included a real case study in the paper, and it perfectly illustrates the tension and the power of this multi-agent debate.
Let me set the scene for this one. A 50-year-old man who has unfortunately been declared brain dead is transferred to the intensive care unit for organ donation. 8 days prior to this, he suffered a massive brain hemorrhage and underwent major surgery. Now, sitting in the ICU, his vital signs are suddenly crashing. His blood pressure is dangerously low. Crucially, he has generalized edema, which is severe swelling, and pink frothy secretions are actively being suctioned from his breathing tube.
It's a dire situation.
And when the doctors listen to his chest, they hear bilateral crackles in his lungs.
From a diagnostic perspective, those specific lung symptoms, the crackles and the pink secretions, are classic screaming red flags.
So the patient's file is fed into the triage agent. The system assigns a pulmonologist bot, a neurosurgeon bot, and a cardiologist bot. How does the AI pulmonologist react to this specific file?
The pulmonologist agent reads pink frothy secretions and bilateral crackles and immediately falls into the anchoring bias trap.
Just like a human might.
Exactly. It diagnoses acute respiratory distress syndrome, or ARDS. It is a very logical, very common deduction based purely on the glaring lung evidence.
It is looking at the muddy footprints. The lungs look terrible, therefore it is a primary lung disease.
In a standard AI system, the process would stop right there. The AI would output ARDS, and the doctors might act on that.
But this isn't a standard system.
Right. In this framework, the multi-round discussion begins, and the counterfactual editing kicks in. The neurosurgeon and cardiologist agents look at the pulmonologist's confident diagnosis and start generating their what-if scenarios to test it.
Okay, so how do they attack the ARDS diagnosis?
The cardiologist agent runs a counterfactual operation, noting that the patient's heart function, specifically the left ventricular contractility, is actually completely preserved according to the file.
Okay.
There is no pulmonary hypertension. So it runs the math and proves that a primary heart failure causing fluid to back up into the lungs is entirely ruled out. The problem isn't the heart.
Got it. And what about the neurosurgeon agent?
Meanwhile, the neurosurgeon agent targets the patient's surgical history.
The massive brain bleed from 8 days ago.
Exactly. The neurosurgeon agent runs a simulation. It essentially says, what happens to our diagnostic confidence if we completely remove the pink frothy secretions and the lung crackles from the file?
So it pulls the Jenga block.
It pulls that exact Jenga block, and the CPG score skyrockets. The math proves that those lung issues aren't the primary root disease at all.
Wait, really? What are they then?
They are actually just downstream secondary physical effects of the massive central nervous system injury the patient suffered 8 days ago.
Oh, wow. Because the brain trauma is so catastrophically severe, the neurological shock is actually what is forcing fluid to build up in the lungs.
Exactly. Because of this explicit evidence testing forced by the other specialist agents, the pulmonologist agent is confronted with irrefutable mathematical proof that its initial anchor was wrong. Here's the incredible part.
Yeah.
It actually changes its mind.
It updates its hypothesis mid-diagnosis.
Yes. The agents reach a new consensus and revise the diagnosis to the correct condition, which is neurogenic pulmonary edema, NPE.
That is fascinating.
It is a severe lung complication, but it is caused entirely by a brain issue, not a primary lung disease.
That is incredible. The AI dynamically corrected its own internal reasoning simply because another agent forced it to pull out a Jenga block and look at the what-if data.
It's a huge breakthrough.
It didn't just double down on its mistake. It realized it was wrong and pivoted. But wait, we can look at probability scores and AI debates all day long. When this is put in front of actual human medical professionals, do they buy it? Do they trust this AI more than the old version?
The researchers conducted a rigorous human evaluation. They had 2 real licensed physicians evaluate the reasoning traces produced by this counterfactual framework, and they compared them blindly to the reasoning produced by standard AI.
A blind taste test for medical logic. I like it.
And the results were striking. The counterfactual framework produced far fewer factual errors, dropping to 37.5% compared to 45.8% for the baseline model.
That's a solid improvement.
It also produced significantly less hallucination, where the AI just makes up medical facts. And it showed far greater completeness in its overall case analysis.
So it is not fabricating data as often, and it is being much more thorough in its investigation.
But the most important metric for real-world application was clinical trust. Ultimately, the human doctors preferred the reasoning and the output of the new counterfactual framework 66.7% of the time.
2/3 of the time, actual licensed doctors looked at the AI's work and said, yes, this machine is thinking like a real doctor.
The evaluating physicians specifically noted that the new framework was vastly superior at explaining why it ruled out alternative diseases.
It showed its work.
Right, it didn't just hand them a final answer. It provided a defensible, deeply logical path showing exactly which symptoms proved or disproved the final diagnosis.
So what does this all mean for the future of how we interact with machines? Let's recap this journey. We started by exploring how anchoring bias is a massive, dangerous trap, not just for human doctors in the ER, but for artificial intelligence. We saw that current language models act like overconfident novices that jump to conclusions and build narratives to protect their first guess.
But we learned that by introducing counterfactual case editing, literally forcing the AI into parallel simulations to systematically remove, mutate, or replace symptoms, we can break that cognitive bias.
We explored the counterfactual probability gap, that CPG score, which mathematically forces the AI to play Jenga with the evidence and prove which symptoms actually hold the diagnosis together.
And we saw that this structured multi-agent debate, carefully supervised by a judge agent, leads to highly accurate decisions.
Right, providing that massive 13.2% boost to smaller models like Llama, which solves the privacy issue by keeping hospital data off the public cloud.
And most importantly, as we saw with the brain-dead ICU patient, this framework allows the AI to do something profoundly human. It allows it to change its mind when presented with better evidence,
Which results in clinical decisions that real doctors actually prefer and trust.
It represents a profound architectural shift. We are moving from an AI that simply predicts text based on patterns to an AI that genuinely verifies evidence through critical self-doubt.
Which leaves us with a pretty wild thought to mull over as we wrap up this deep dive. If we can successfully train AI to use counterfactuals to escape anchoring bias in high-stakes medicine, what other critical fields could be completely revolutionized by coding self-doubt into the machine?
Oh, the possibilities are endless.
Imagine an AI financial advisor that isn't just a yes man, but is explicitly programmed to actively argue against its own initial investment assumptions before it ever gives you advice on your retirement. Or imagine a legal assistant bot that has to run thousands of what-if simulations to try and actively break its own case strategy before a lawyer ever sets foot in a courtroom.
It changes everything.
If doubting yourself makes you a measurably better doctor, maybe programming self-doubt is the ultimate secret to making AI better at, well, absolutely everything.